Hello.
Sir,
Hello. Hello.
Sir, it's audible, sir.
Yeah, ma'am. Go ahead, ma'am, please.
Okay, we'll start, sir. We'll start. Hello, everyone, and welcome to today's session. I'm also pleased to welcome today's resource person, Dr. Prakash J, Professor, Department of Instrumentation Engineering, MIT Campus, Anna University, Chennai. Welcome you, sir. I'm also happy to welcome all the participants for the fourth day of the AICTE-sponsored 2-week faculty development program on cutting-edge trends in deep learning approaches. Today, our resource person is Dr. Prakash Che. He is having more than 25 years of teaching and research experience. He has published more than 40 research articles in the peer-reviewed national and international journals. He delivered invited keynote lectures in the international conferences, invited lectures in pre-conference tutorials, workshop, faculty development training program, etc. He contributed for the establishment of state-of-the-art field bus laboratory at MIT campus, Anna University, first of its kind in an educational institution in India. He carried out collaborative research in international level with Computer Process Control Group, Department of Chemical and Materials Engineering, University of Alberta, Canada, in the area of state estimation and data fusion and particle filter for state and parameter estimation in constraint process. Now I request Dr. Prakash J, Professor, Department of Instrumentation Engineering, MIT campus, Anna University, to share this experience with us in the topic of data-driven model and machine learning. Now the session is yours, sir.
Thank you, ma'am. At the outset, I would like to thank Congo Engineering College for having given me this opportunity. In my today's presentation, I'm going to primarily focus on how to build models from data. So given the data, that is the input and the output data, how to build models and validate models. That is my primary focus. And I understand that participants are from different backgrounds. So in the first part of my lecture, it's going to be very generic, and I'm not going to focus on any specific system so that everyone will be benefited. So as a result, I'm going to take some general simple examples so that everyone can understand the first part of the lecture. But in the second part, since I have worked extensively in the field of chemical engineering, so the example that I've chosen is a chemical engineering example. But however, I will explain in detail about the process. Once everyone knows about the process, then it's easy to follow. So in the second part of my lecture, I've taken a chemical engineering example, but I will explain in detail about the system so that everyone can understand the second part of my lecture. And in the third part, again, it's very generic, but in all the three parts, my focus is to build models and validate models. Of course, you can use different techniques available to build models, but I'm going to focus on machine learning, and of course, whether we build model using machine learning techniques, like certain things we have to follow scrupulously, and so that I would like to cover in the first part of my lecture, so that we can build accurate models, and thereby we'll be able to carry out accurate predictions. So that with that perspective, I'm going to cover my first part of a lecture. So in a nutshell, what I can say is at the end of the lecture, like everyone will understand and how to build models accurately. That's the primary outcome will be the primary objective of this lecture. So let me once again emphasize that learning relationship between inputs and outputs from training data will be the focus. Basically, we want to build the relationship, how inputs and outputs are related. So learning relationship between input and outputs from training data, that is basically the machine learning algorithm. And as I mentioned earlier, the focus is on building models. So a model is a representation of an actual system, or I would say an abstraction of a real system. And we want to build a relationship between variables, between input variables and output variables. And so basically a model is going to learn the relationship between inputs called features in machine learning. In machine learning, inputs are called features. So a model learns relationship between the inputs called features and output called labels. So in machine learning parlance, inputs are called features and outputs as labels. So basically we want to build a relationship between features and labels, and thereby we can do prediction, classification, whatever we want to do, we'll be able to do. But I'm going to focus on the regression aspects. That is basically we want to build models, and thereby we'll be able to predict the output. For example, in the case of weather forecasting, or I would say financial forecasting, where we will build models and then predict how the temperature is going to change over next 2 weeks, 1 week. So something like so that, and then we'll be able to take action, corrective action, early corrective action. So that's the primary focus. And in other words, what we can say is basically what is our interest is function approximation. So function approximation is a technique for estimating the unknown function f. So here in this slide, if you see, there are m inputs. So u belongs to Rn. I'm assuming that there are m inputs and n outputs. Y belongs to Rn. So there are n outputs and m inputs, and we are trying to relate this n outputs with m inputs. So that's the primary focus. And so y is a function of u. So there are m inputs, u1, u2, um, and n outputs, y1, y2, and they are related through a model, like some relationship. And the model could be a static model, or it could be a dynamic model. So we can build and the governing equations of a static model is an algebraic equation. Here I've given 2 examples. Y of k equal to w1 times u of k plus w0. This can be viewed as y equal to mx plus c, where y and x is your u of k, and your m is w1, and your c is nothing but w0. So w0 and w1 are considered, you can imagine it as basically weights. In neural networks, if you see w0 and w1 are considered as basically weights. Or the coefficient of u of k and a constant, w0 can be considered as a constant. So and in the second example, y of k equal to u squared of k. So the square of the input here, the square of the input, u is the input, square of the input at discrete time instant k, that is basically is used as a mapping function. This is basically a mapping. So your f of u is nothing but u squared of k. So basically I want to build a relationship such that what will happen, y of k equals u squared of k. That is our interest. Either it can be represented explicitly in the form of an equation y of k equal to u squared k, or you can represent in the form of a network, in the form of a neural network. Or deep neural network, or whatever conventional neural network. So you can represent the same. You can either build an explicit relationship or an implicit relationship relating inputs and outputs. If it is a dynamic model, y of k not only will depend on yk minus, so it will depend on its past values, yk minus 1 and uk minus 1, uk or uk minus 1. So y So y is a function of yk minus 1 and uk minus 1. So in the case of a dynamic model, here I would say it's function of y squared of k minus 1 and uk minus 1. So it could be linear or non-linear. Basically our interest is to determine the relationship between inputs and outputs. For example, here 0.9, 0.1 are considered as weights, which we will determine through what I would say training, and then by training, what I mean is we wanted to estimate the coefficients of yk minus 1 and uk minus 1, y squared k minus 1 and uk minus 1. So our interest is to find W1, W0. That's our interest given inputs and outputs. So in order to build a model, one has to conduct test. First, you have to conduct test on the experimental setup, the system under consideration. So we have to conduct test on the experimental setup where we have to excite the system, and then with the help of a sensor, we have to acquire the data. And through data acquisition system, the data has to be taken inside your PC, personal computer. So we need a data acquisition system, and with the help of a data acquisition system, we'll be able to acquire the data, that is your input as well as output data, into the computer. Once you have the data acquired from the system, then what one has to do, what is called a post-processing. So first we have to acquire the data. So that's a raw data which is acquired from the system with the help of sensors. Like we have to deploy sensors on the systems. So depending upon the type of systems, we have to install right type of sensors, and then one has to excite the system. You have to give inputs, and then the system will respond to that input, and the sensor output has to be interfaced with the personal computer system through a suitable data acquisition card and all. So you need a data acquisition system is basically required to acquire the data from the physical system. And once you have the data, that is the raw data that is available. But before feeding that raw data into like, for example, neural networks or deep neural networks, first you have to do data processing. Processing is very, very important, where in the data pre-processing, our focus is to suppress the noise, because when you acquire the data from the sensor output will be corrupted by noise. So you have to design a suitable filter, and then you have to cull out the measurement noise. Or sometimes, if it is a wireless transmitter or a wireless sensor network, then there is every possibility that because of connectivity issues, the data, some of the at certain time instant, the data may not be available. So which we call it as missing data. So if the data is missing, again, what we have to do is that we have to use suitable algorithm and then detect the time instant at which data is missing, and then we have to do a data imputation. So that's called data substitution. So first, we have to detect missing data, and then we have to do data imputation. If the sensor output is corrupted by noise, we have to design suitable filter. We have to cull out the measurement noise. Or sometimes what we have to do is that if missing data, or it could be sensors, or sometimes what will happen, there could be some problems in the sensors. For example, there could be bias in the sensor, maybe because the sensor is not properly calibrated. Maybe the output of the sensor would not indicate the true value. So sometimes what we have to do is that we have to recalibrate the sensor, and in certain circumstances we have to detect outliers. We have to detect outliers and we have to remove outliers. So the raw data asset should not be used for building model. I wanted to convey that to the audience. So we have to do data pre-processing. That is what we call it as data analytics. Process data analytics. We have to pre-process the data, and then the raw data has to be pre-processed, and the pre-processed data only has to be used for building models. And so using the input and output data, our interest is to find this unknown function f. This f you can you can represent in form of a neural networks. This F may not be an explicit relationship like this. This F could be a neural network model which relates input and output. So it need not be like y of k is u squared of k, but I'll try to represent this u squared of k. I'll try to capture this u squared of k using with the help of a neural networks or a deep neural networks. So our focus is basically on this function approximation. We don't know this f, and our interest is to approximate this function f, that is the unknown function, using the input output data. So that's the like now in my subsequent slide, I'm going to focus on how to build models using the pre-processed data. I'm not going to focus on how to remove outliers, how to cull out measurement noise, data imputation, like how to carry out data imputation. All that I'm not going to focus in my today's lecture. But however, one has to do this before building models. And what is important here is, so basically our interest is to build accurate models, and thereby we'll be able to carry out accurate predictions. That's our primary focus. So for that, what is important here is the important thing is here everyone should understand this concept of bias variance trade-off. This is a very important concept. Like if you're trying to build a model, whether you use neural networks or deep neural networks, everyone should understand this bias variance trade-off. So here in this slide, what I've explained is the concept of bias variance trade-off, where if you see this figure, the x-axis, that x label is model complexity, and your y label is basically the error. So when you try to build a model, definitely the one will not be able to capture the true model. One cannot build a true model. Always there will be an error. And what is our interest is basically to minimize that error. That's our focus. So the total error in the model is a combination, I would say, of three components. The three components, the first component is your bias, the second component is the variance, and the third component is the irreducible error. So we cannot avoid error. Definitely there will be a mismatch between the actual system output and the model output. But basically what we wanted to say, we want to minimize the error. That is our focus. And let me emphasize here that total error is a combination of three components: bias squared, variance, and the third part is the irreducible error. So now what? So here, what is important here is, if you see here, if I increase the complexity of the model, as the model complexity increases, what I mean by that is, let's say you're using a neural network with a single hidden layer. If you use 2 hidden layers, if you use 3 hidden layers, let's say, or more than 3, then the complexity of the model increases. That is what I mean by here. So the model complexity increases as you increase the number of hidden layers in the neural network. So as a result, what will happen? So basically, if you increase the complexity of the model, if it get increased, then what will happen? The bias will reduce. So the first part. So you can reduce the bias by increasing the model complexity of the complexity. But on the other hand, what will happen is the variance will increase. So here the important part, like everyone should know, is bias will reduce. The first component will reduce, bias squared. If you see here, that will reduce, but the variance will increase. So as a result, what will happen? Your total error will increase. So you can see this optimal model complexity, which that's a demarcation line. To the left of that, you can say, to the left of this demarcation line, this dotted line, vertical line, to the left, what you see here is the variance is high. Variance is low. Sorry, the variance is low. The variance is low. On the other hand, your bias is high. So if the complexity of the model is very low, then bias will be high, but variance will be low. On the other hand, if you try to reduce the bias, then what will happen? the variance will increase. So on the to the left of half of this demarcation line, variance is low, bias is high. On the right side, if you see, bias is low and variance is high. But as a result, the total error, if you see, total error is it's increasing. But what is important here is like when we try to build a model, we have to find an optimal model structure, meaning like the number of hidden layers. So you should not arbitrarily choose. So we have to come up with an optimal number of hidden layers such that what will happen, the complexity of the model is also optimum, and as a result, your total error will be minimum. You can see here. So at this point, only the total error is minimum, where these two lines they intersect actually. The variance and bias they intersect. So at that point only you get lower error. So that corresponds to a particular like I would say that is basically the optimal model. For that, so one has to identify that. That is more important. So that's what I wanted to here emphasize. So you should not arbitrarily increase the number of layers in the neural networks to reduce the bias. But what will happen? The variability increases. You will not be able to. So that's the problem. So that's here the emphasis mainly. So like through training, you have to identify the optimal model structure, and then you have to estimate the parameters associated with the model structure. Estimating the parameters associated with the model structure is basically the weights between the input layer and hidden layer, weights between the input layers and subsequent hidden layers and output layers. So there are weights actually. So you have to estimate the weights. Estimate the weights associated with the model structure. So that is our focus. And then here, if you see in this slide, there are two figures. There are two, and on the right side, if you see, is a complex model, and on the left, what I had mentioned is a simple model with respect to the complexity. Complexity, it's a very low complexity. On the right side, what you see is a very complex model. So, and if you see the complex model, this model is able to capture every change in the data. So the spread of the data point is your the red ones are the spread of the data points, input-output data points, and the model is able to capture every change in the data, every change. As a result, what you get is here. If you see here, this is what we call it as overfitting. Overfitting. As a result, your variance, the variability will increase. This is on the right side, right-hand side of this demarcation line, the vertical line. So what you get is, if you increase the complexity of the model is able to capture every change in the data. It's able to capture. As a result, it leads to overfitting, and the bias will reduce, but the variance will increase. On the left side, if you see, the model is not able to capture every change in the data. It's not passing through. It's a simple line which is not passing through the origin. So y equal to mx plus c is a very simple model. Y equal to mx plus c. It's a straight line not passing through origin, and you can find the slope and the constant. That is basically the bias you can count. So as a result, the model is not able to capture every change in the data. You can see that there is all the points are not lying on this line. So there is some difference. So this is what we call it as a bias. So bias is more, but variability is less compared to these two figures. So this leads to, if you use a low complexity model, then you will have we will end up in underfitting. We are not so underfitting of the model, whereas on the other side, what you see is overfitting of the model. But what is important here is we have to avoid the mistake of overfitting and underfitting. You have to avoid both underfitting as well as overfitting. So when you try to build a model, this you have to take into consideration. So we need an optimal model whose complexity, like it should not be too complex or too simple. That is very important. So in other words, we have to avoid, there are 4 possibilities because there are 2 factors, bias and variance of the 2 factors. So there are 4 possible combination, and we have to avoid. The first one is high bias, high variance have to be avoided. High bias is not acceptable, and high variance is also not acceptable. What is acceptable is low bias, low variance. That is our interest. One has to build a model such a way that it will yield low bias, low variance. And we have to avoid high bias and low variance, which I said is underfitting. This is because of you have assumed a simple model structure, which is unable to capture the static and dynamic behaviors of the system. It's unable to capture the relationship. So as a result, it leads to underfitting. So we also have to avoid high bias and low variance, and low bias and high variance, which is basically a complex model with several hidden layers. So there are too many parameters, which leads to overfitting, or the model will capture every small change in the data. As a result, bias will be low, but variance will be high. So let me repeat again, we have to avoid underfitting, we have to avoid overfitting. High bias and high variance also have to be avoided. So our interest is to build a model such a way that it will yield low bias and low variance. And so the same concept which I had explained in the previous slide, that here one can visualize this bias variance trade-off using bull's eye diagram. So here it's the same thing. So low bias, low variance, low bias, high variance, high bias, low variance, and high bias, high variance. And if you see the center part, the center one, that is basically the true value. But if you, in the case of low bias, the predicted value will be close to the true value. The center one is the true value. So a model will predict the predicted output of the model. If it is lying close to the true value, then we say that the bias is low. Bias is low. If it is lying close to the actual value, if the predicted output, if it is exactly same as that of the actual output, then what we say is that then it says the bias is very low. And if you see the spread for different values of inputs, you will get corresponding outputs. And if you see the spread of the data points, they are lying close to each other. As a result, it yields low bias and low variance. On the other hand, on the right side, if you see the spread of the data points, if you see they are not lying close together, close to each other. So as a result, variance is high. But if you take the expected value of all this data point, then that expected value, average value, will be close to the true value. So the average value of all the data points, if you take that average value is lying close to the true value. But the spread of the data points, if you see, they are not lying close to each other. So as a result, it yields low bias but high variance. Variability is very high, which is not acceptable. The third combination is high bias, low variance. So the data points are lying far away from the center value. So the center value, but the spread of the data points, if you see, they are lying close to each other. So the spread is less, but the data point is lying far away from the true value. So as a result, it will yield a high bias. The last combination is basically neither the data points are lying, the average value of the data point is lying close to the actual value, and the spread of the data points also, if you see, they are not close to, they are not lying close to each other. So the spread is large, and the average value, the expected value, is not lying close to the actual value. So that's the problem with respect to high bias and high variance. So one can visualize this bias variance trade-off using bull's eye diagram. So what is our interest is, what we want is, we want to build a model such a way that if you predict the output for different values of inputs, what one should get is the first part, that is low bias and low variance. As a result, the predicted output will lie close to the true value, and the variability associated with the output also, it will be less actually. Less variance, bias also it will be less. It should be less. That is this is a very important concept, irrespective whether you use neural networks or you use fuzzy logic to build models or you use deep neural networks, irrespective. Or let's say you're trying to build a first one, or like some data-driven models, like you will propose a model structure and you try to estimate the parameters, not using neural networks, support vector regression, or it could be combination of neuro, fuzzy, whatever be. Irrespective of whatever be the structure of the model, neural networks, fuzzy logic, neuro fuzzy, SPR, or some other combination. But what is important here is, this is a very important concept. One has to take this into consideration, and they should build a model in such a way that it will low bias and low variance. And in the literature, in the research literature, there are many techniques proposed to reduce bias and variance. So there are in my lecture, so I'm going to focus on this, how to reduce this bias and variance, and for which there are many techniques available. The most preferred one is the regularization. So with the help of regularization, one can reduce bias and variance. Through a simple example, I'm going to demonstrate this. So you please wait. So that's how to reduce bias and variance. And there are other emerging techniques called bagging, boosting, stacking, which belongs to ensemble learning. This is in machine learning. So using this ensemble learning technique, machine learning techniques, one can can reduce this bias and variance. And for that, there are three different concepts proposed in machine learning literature: bagging, boosting, and stacking. I will explain the concept. I'm not going to explain in detail about this, but it's a very it's very intuitive. I through some block diagram, I will try to explain the concept of this bagging, boosting, and stacking. So this is a very and thereby what you can do is that one can reduce this bias and variance. Now the focus will be on like how to reduce this variance. So I'm going to take a very simple example. In that example, my input is X, but it can be U also. But here I've taken input as X, but in the earlier slides and all, I've treated input as U. It can be X. So input is X and output is Y, and they are related through this equation y equal to f of x. Y equal to f of x is basically the relationship between x and y. But I don't know this f. And x belongs to R, y belongs to R implies that x is a scalar and y is a scalar. So meaning there is only one input and one output. So I wanted to relate that one output with an input, the corresponding input. And I'm assuming that there are n observations because I need data. Without data, one cannot build model. So I'm assuming that there are n observations. Using this n observation, that means there are n different values of x. So n values of x are there, and corresponding to that, I have n values of outputs: x1, x2, xn. And for different values of x, the corresponding of y is also available. I'm assuming that data are not missing. No missing data, no outliers. So I'm assuming in my presentation. And the other important here is the input-output data. So I've acquired the data, and here the plot. That is the data visualization. You can see how x and y are related. So what is important here is, after having acquired the data, one has to plot the data. So you have to so a graphical representation is what is required. So that is what we call as data visualization. You visualize the data, and from the data visualization, one can infer whether data is missing or there could be outliers, noise. All that can be figured out like through this data visualization. So from the plot, one can infer that the relationship between input and output is not linear. It's obvious. So it's not linear, and so there exists a non-linear relationship between input and output. So as a result, we have to find out that, capture that non-linear relationship. That is our interest. So there are 10 observations for training. I'm using 10 observations. For testing, so what we call it as a validation. First, I'm using another 10 observations. So 10 observations for training the model, and another 10 observations for testing the model. So you have training and testing, or what we call it as training and validation. Building a model using the training data, and validating the model using the test data. So there are 10 observations. The X and Y values are here shown, and similarly here for the test data points, the X and Y values are reported or presented, I would say, inputs and corresponding outputs. So I have 10 observations and for testing, and 10 observations for training. Now, what I'm going to do is to demonstrate this concept of this bias variance trade-off. The approach which I'm going to use is the simplest approach, is like the least squares approach. Through this least squares approach, I'm going to explain this concept of bias variance trade-off. So Y is here, if you see, this Y is basically the output of the system. So Y is available, Y is known. Y tilde is nothing but the model output, Y tilde. So, and I have assumed a model structure. M1 is the model structure. Y tilde is W1 times X plus W2 to X square plus B. You can assume like this, or you can represent this in the form of a neural network. So either this can be represented in the form of a neural network, or you can assume propose a model structure. This is basically a polynomial type of model. Y tilde is W1X plus W X square plus B. Or the same thing can be realized in the form of a neural network. So W1X plus W2 X square plus B is the model which I have proposed. And here the unknowns are the coefficient of X W1, coefficient of X square W2, and the constant which is B. When X is equal to 0, Y tilde will be B. That is basically the constant. Y tilde will be B. So that is your B. So B, W1, W2 are the parameters associated with this model. I have assumed this model, so I'm guessing. Basically, I've guessed. After having visualized the data, I've guessed, and I'm proposing this model structure, W1X plus W2 X squared plus B. And for different values of X, if I know the value of W1, W2, and B, if I know W1, W2, B, one can determine what is the value of, one can determine Y tilde. That is nothing but the output of the model. So I'm assuming, and what is our interest here is, we wanted to minimize, so my objective function is basically, I want to minimize the sum of squared error. This is your actual output from the system, minus the model output squared. So over N1 observations. I'm assuming that there are N1 observations. So sum of squared errors. If there are N1 observations, for each data point there will be an error. I want to minimize that error and determine W1, W2, and B. So by minimizing the sum of squared errors, I want to determine W1, W2, and B. So in the case of a neural network also, neural network will generate an output Y tilde. So I want to minimize this, the difference between the output from the system and the neural network output, such a way that I'll find the weights between the input layer and hidden layer and output layer. So the weights are nothing but here W1, W2. They are nothing but the connection weights. So you can imagine, instead of this M1, I'll use here a neural network, and I'll apply the input X, and it will generate an output Y tilde. So X is the input to the neural network, and Y tilde is the output of the neural network. Instead, I've assumed an explicit relationship W1X plus W2 X squared plus B. So I'll plug in for Y tilde. So yi minus W1 X squared minus W2 X squared minus B the whole squared. Here the unknowns are W1, W2, and B. And X is of course known. X is known, Y tilde, okay, we don't know W1, W2, and B. So by minimizing this objective function, this cost function, one can determine W1, W2, and B So that's one can refer to any standard textbook. That's the famous least squares approach, where using the famous least squares approach, one can determine the unknown parameters W1, W2, and P. So this is what we call it as training. Using the training data points, I've estimated the unknown parameters W1, W2, and P. In the case of a neural network, the connection weights. So this is the conventional least squares approach. Now, I'm going to focus on the concept of regularized least squares approach. In the regularized least squares approach, in addition to in the cost function, we have used sum of squared errors. In addition to the sum of squared errors, I'm going to add a penalty function. The model structure remains same. I'm going to use the same model structure, but I'm adding some penalty function. There are different types of penalty function available in the literature. So depending upon the type of penalty function, the regression approach has been classified as ridge regression. In the ridge regression, the penalty term is proportional to the square values of W. Square value. This is what we call it as 2 norm, square values of W. And in the case of Lasso, least absolute shrinkage and selection operator, absolute values of W. That will be my penalty function, absolute value of W1, which we call it as norm 1 norm. This is 2 norm. 2 norm and 1 norm. And in the case of an elastic net, it will be a linear combination of 2 norm and 1 norm. Alpha times 2 norm plus beta times 1 norm. So in addition to in the objective function, there are 2 terms. The first term is basically sum of squared errors, and the second term is the penalty function. In the case of ridge regression, we will use this. In the case of Lasso, we will use this as a penalty function. In the case of elastic net, we will use the third one, which are highlighted in red. So first, let's focus on the ridge regression. We are going to add that penalty function. As a result, our objective function will get modified. So our objective function will be gamma times W1 square plus W2 square, because there are 2 weights W1 and W2. We won't use this B naught in the penalty function. And this gamma is basically, it's called a hyperparameter. In machine learning, they call gamma basically a hyperparameter. And this hyperparameter, one can estimate this hyperparameter using cross validation, 5-fold cross validation or 10-fold cross validation. So W1, W2, B are called parameters. Gamma is nothing but a hyperparameter. But we normally will assume through cross validation, we will find the optimal value of the hyperparameter. Here in this case, gamma. But the same model structure, but in the objective function, I've added this term. That is gamma times W1 square plus W2 square. In the case of a Lasso approach, also the objective function is modified. It's basically gamma times modulus of W1 plus gamma times modulus of W2. So this gamma is common to both W1 and W2. Gamma times absolute value of W1 plus gamma times absolute value of W2. So this is our penalty function. And in the case of an elastic net, it's a linear combination of that is your 2 norm and 1 norm. I said alpha times W1 square plus W2 square plus beta times absolute value of W1 and beta times absolute value of W2. So alpha times W1 square, alpha times W2 square. And this alpha and beta, they are considered as hyperparameters. So in the case of ridge, gamma is hyperparameter. In Lasso also, gamma is hyperparameter. Whereas in the case of elastic net, there are 2 hyperparameters, alpha and beta, which one has to determine using this concept of cross validation. So sum of squared errors plus penalty function. Now, so using this regularized least squares approach or the ordinary least squares approach, one can estimate the unknown parameters W1, W2, and P. Irrespective of whether we use the conventional least square approach or the regularized least square approach, that is ridge or Lasso or elastic net, the number of parameters to be estimated is same. There are 3, only W1, W2, and P. There are 3 parameters to be estimated. So that is the parameters associated with the model structure. And let's assume that through the regularized least squares approach or conventional approach, we have estimated the model parameters. That is W1, W2, and P. So that means we have W1, W2, and P. Now, what is important here is we have to do a validation. After having estimated the parameters of the model, we have to do a validation. And through validation, we are going to assess the quality of the fit. The fit, whether it is 100% fit, 50%. So the quality of the fit is what we want to assure. We wanted to ascertain. So for that, the performance measure that is used is mean square error. With the help of this mean square error, we can assess the quality of the fit, model quality fit. So here I've given the relationship. This is basically your output of the system, and y tilde is your output of the model. And then here again we have assumed that there are n1 observations. And we take this term is nothing but sum of squared error divided by number of data points. So this is basically mean squared error. We call it as mean square error using the training data points. Similarly, using the validation data point, that is test data points. So using the test data point, you can compute again the mean square error. So we have training data points and test data points. We can compute this mean square error using training data points. We can compute again the mean square error using the test data points. So we have training error, testing error. Two things are done. So the first step is what we have done is we have proposed a model structure. We have estimated the parameters of the model using regularized least squares approach, conventional least squares approach. Then the next step is what we have to do is that we have to assess the quality, model quality fit. For that, we have to compute this mean square error using training data points and the testing data points. So as a result, we have training error and testing error. And in this slide, what I've shown here is the results using three different approaches. That is ordinary least square, conventional least squares approach, ridge regression, and lasso. And in the first column, I have reported the number of observations. So in the first row of the first table, second row of the first table, if you see, I have used 10 observations. Then I have reduced from 10 observations from 10 to 5. I've used 5 and estimated the parameters of the model. Further, I have reduced the number of observations to 3. So 10, 5, 3. In the second row, I've used 10 observations. In the third row, 5. And in the fourth row, if you can see, I've used 3 observations. Similarly, for ridge regression also, 10, 5, and 3. In LAS also, I've used 10, 5, and 3. And in the second, third, and fourth column, I've reported the estimated value of the parameters of the model. That is W1, W2, and B. So W1, W2, the estimated values are reported here. And in the last column, the testing error, that is mean squared error using testing data point. Last but one column, the mean square error using training data points. So training error, testing error, and the parameters estimated using least squares approach for different data points are reported. Similarly, in the second table also same thing, but using a different technique, that is ridge regression technique, and using a lasso. So first, let's interpret the first table. So you can see that if I use 10 data points, then you can see here the training error and testing error are almost same. Training error is 0.13 and testing error is 0.12. As a result, they are almost same. On the other hand, if I reduce the number of observations, instead of using 10, if I use 5 data points, you can see there is a drastic difference in the training error and testing error. Testing error is found to be substantially higher than training error. So you get the model quality, like how to interpret this point. So your model is able to capture every change in the data. If I use the training data, so as a result, it does like overfitting has happened. Because of overfitting, if you apply a different inputs, a new set of inputs, then the predicted value is not exactly matching with the true value. So this leads to what we call it as overfitting. Because of overfitting, the testing error is higher than training error. Further, if you reduce, also you can see that there is a substantial increase in the testing error. 494 compared to 3.2 e power minus. So training error is low, very low, but whereas the testing error is very high. On a new day, if I feed new inputs, which was not presented at the time of training, then the predicted output is not exactly matching with the actual output. As a result, your testing error is very high. So this has to be avoided. On the other hand, if I use a ridge regression, again you can see if I use 10 observation, testing error and training error are almost same. But if I reduce the observation, of course, testing error and training error, they are not matching, but relatively compared to the OLS approach, the testing error is not that high compared to the training error. Further, if you reduce this, testing error increases, similar to that of OLS. But relative to OLS, the performance, if I add the penalty function, then I'm able to reduce the error. I'm able to reduce the variance. That's the power of this ridge regression. And in the case of Lasso, if you see, if I use 10 observation, same thing, more or less, the validation error and testing error are almost same. But if I reduce the number of observation from, and if I use only 5, you can see here, relatively not that high compared to what I would say ridge regression and OLS. And if I reduce further the observation, of course, testing error and training error, the validation error is increasing, but relatively, if you see compared to the previous techniques, ridge regression and OLS, Lasso is performing better. So as a result, and one can notice here, the value of W1 is 0, irrespective of whether you use 10, 5, or 3 observation. Whereas in the case of ridge regression and in the case of OLS, we're getting non-zero values of Y. Non-zero values of W1. Whereas here, so, and W2, if you see, almost it is 1 actually. 1.004, 1.0059, 0.932. Almost W2 is 1. And this B is also almost close to 0, 0.05. And so as a result, this Lasso is able to figure out that model is not at all dependent on X. It depends on only X squared. So as a result, even though I have assumed, I have proposed a model structure W1 times X plus W2 X squared plus B, but Lasso is able to figure out that model does not depend on X. As a result, W1 has become 0. So Y tilde is W2 X squared plus B. So I have proposed a wrong, I've assumed a wrong model structure, but the algorithm is able to figure out that Y tilde is not function of X, it depends on only X squared plus B in the case of a Lasso. Irrespective of the number of observation, W1 has become 0. And because of this reason, OLS and ridge regression, if you see ridge regression, there is a mismatch in the structure. As a result, the actual output and model output are not matching. That's the power. So thereby we were able to, so using Lasso, we were able to reduce the bias as well as the variance. So as a result, what we got was a model which will yield low bias and low variance. That's the power of this particular technology, power of this approach. Reason why I have reduced the number of observations, because in certain application you will not be able to, you won't have large data. Though we say big data analytics and all, but in every application you won't get large data. You may get, you will not be able to conduct tests and collect more data. So as a result, number of observations will be very less. So in those circumstances also, one has to generate an unbiased estimate, unbiased minimum variance estimate. And you can see here, Lasso, irrespective of the, even if I use 3 observations, is able to estimate the values more, I would say, more accurate estimates Lasso is able to generate compared to ridge and OLS approach. And so through this concept of regularization, I've explained how to reduce the bias and the variance. Next, what I want to focus here is we have to estimate the hyperparameter, which is gamma, for what value of gamma you'll get low value of bias and variance. One has to find out. So for that, we have to resort to what is called cross-validation, and five-fold cross-validation is the most preferred one. So in the five-fold cross-validation, of course, the performance metrics remain same. The performance measure which we are going to use is the mean squared error. Like we are going to compute the mean square error. So the entire data set, earlier I said we have to split into training and testing. Instead here what we are going to do is we are going to split the data set into five folds. The whole data set I'm going to split into five folds. First fold, second fold, third, fourth, and fifth fold. So the green one is basically the test data. The remaining one, the yellow ones I'm going to use as training data. And then I'll try to build a model. Then compute the mean squared error using the estimated parameters of the model. Then I'll use the second block, second one as basically my test data set, the remaining one as my training data set. Then I'll estimate the parameters, then compute my performance metric mean squared error. Like that I'll do in the third, fourth, and the fifth iteration. So I'll estimate the parameters. Then I'll compute what is called the generalization error, which is nothing but the average value of the mean squared error. So that is computed error, the first one E1 plus E2 plus E3 plus E4 plus E5 divided by 5. So 5, because I have 5 iterations are there. So for different values of gamma, I'll compute this generalization error for gamma 1, gamma equal to 1, gamma equal to 2, and gamma equal to 0.5. And then I'll find out for which value of gamma the generalization error is low. So I'll plot a gamma versus generalization error. And for different values of gamma, that is x-axis, I'll plot the generalization error. For one particular value of gamma, you will get a minimum value. So that is the optimal value. So I will use that, and then what I'll do is that I'll find out, I'll substitute that value and then find out what is then I'll estimate the parameters of my model, that is W1, W2, and B. So thereby through cross-validation, one can determine the optimal value of gamma. And of course, if you have different data sets, one can also experimentally estimate bias and variance. So this is the first data point, different values of x and y. Similarly, this is the second data point. So using the first data point, I'll estimate the function f1. Using the second data point, I'll estimate f2. Third data point, I'll estimate f3, and fourth data point, I'll estimate f4. So and then I'll find the bias and variance using this relationship. You can substitute the values for your f tilde. You can compute f tilde using this f1 tilde, f2 tilde, f3 tilde, and f4 tilde. Once you have this f tilde, then you can find what you can, and the true function, because in simulation you know the true value of f of x, so you can estimate the bias as well as the variance. So using this relation, I'm assuming that I know the exact relationship between input and output. So that is basically your f of xi, and f tilde xi is nothing but your model output. So one can find the bias is nothing but the difference between the true value and the actual value. So one can estimate the bias as well as the variability. Experimentally also it's possible. And then you can compare the performance of various methods. And what is more important here is you have to use a method which yields low bias and low variance. So far what I have my focus was to how to build models to reduce variance and bias using the concept of regularization. Then I said one can also use ensemble machine learning techniques such as bagging, boosting, and stacking, and reduce the bias and variance. So first, now I'm going to explain how to use bagging and then reduce the variance. And Here, if you see, I'm assuming that the initial data set is available. From the initial data set, I'm going to generate L bootstrap samples. This is my first zeroth iteration, first iteration, Lth iteration. So I have L plus 1 bootstrap samples are available. So I have L plus 1 data sets. From the initial data set, I'm going to generate L bootstrap sample is using each data set. That is zeroth data set, first data set, Lth data set. I'm going to build a model. So, and thereby using different data sets, I'm going to build a model. So I have a bank of models. This could be a neural network. This also could be a neural network. This also could be. So I have a bank of neural networks using the corresponding data points, training data points. So I have L plus 1 training data points. So I'll build models. Then what I'll do is I'll try to combine these models. So the output of all these models will be combined, and we will take the average of the model output. So here basically I'm doing what I'm doing this here. Here I'm doing an averaging. Take all the outputs, sum, and then like average means like sum all the outputs and divide by the total number of models. So and thereby with the help of this, what I can achieve is I'll be able to reduce the variance, the variability. That's the power of this technique. So I'll try to build I'll do a overfitting. I'll try to build a complex model. The model complexity will be high. As a result, what will happen? The variability will be very high. So what I'll do is, in order to reduce the variability, I will construct bank of such models and then try to, with the help of an averaging, I will reduce the bias. That is the concept of bagging. So in bagging, what we have to do is we have to generate this bootstrap sample from the data set. Let me explain how to generate that bootstrap sample. So my initial data set, if you say there are 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 12, these are the values. So from this data set, I'll randomly draw 5 samples. Randomly, I'll draw samples from this bag. 1, 10, 3, 8, 3 are the values drawn from this bag. Then what I'll do is that then the samples which are drawn from the bag, again what will happen, I'll replace, I place it again in the same bag. Then I'll generate the second data set. For the second data set, again I'll draw 5 samples from this bag. So 4, 2, 11, 9, 3. That is my second training data points. Like that, one can generate L or L plus 1 data set, each of size 5. Here, 5. There are 5 observations in each data set. Number of observations is 5. So using this data set, I'm going to build model. For each data set, I'll build a model, a neural network model, and then try to and each model will generate an output corresponding to the input, and I'm going to combine all these output. A weighted average of all these output is nothing but the output of that is the actual output. That is called the concept of bagging. And in stacking, same concept I will use. I won't generate L bootstrap sample. I use the same data set in all models. But here, the models need not be homogeneous. It can be heterogeneous. Meaning I can use neural networks. I can use support vector machine. I can use some polynomial type models. Models need not be same. It can be heterogeneous. Or I can use here an RBF neural network, or I can use a feed-forward neural network, or I can use a deep neural network. So in stacking, the structure need not be homogeneous, it can be heterogeneous. The same data set will be used in all, used to estimate the connection weights and the hyperparameters associated with the models. And then all the outputs are combined. Okay, so where you get the average of all the outputs. That is basically, this is what we call as a meta model. So, and thereby what you can do is that you can again minimize the variance. Of course, I've not explained the concept of boosting. In boosting, what we do is we sequentially train the model. In bagging, we do parallelly we train the model. using the respective data set. In case of bagging, we'll use the corresponding data points. In the case of stacking, we'll use the same data points but different model structure. So parallelly, what one can do a training and estimate the parameters of each and every model structure. Whereas in boosting, what we do is that sequentially we build models. And thereby what we do is that we reduce the bias and variance. So there are different methods available. In boosting itself, there are many techniques available, ADA boosting. So there are different techniques. In stacking also, there are different approaches available. One has to refer literature. So using this concept of boosting, bagging, and stacking, one can reduce the bias and variance. That's the focus. That is what is important, because we have to build a model which will generate low bias and low variance. So with this, I've completed the first part of my lecture. That is, in the first part, my focus was on how to build models, validate models, and the model should yield low bias and variance. If there are any questions I would like to answer, then I'll move to my second part. Are there any questions? Audience, if you have any questions, you can post. I'll be able to explain. So here my focus was not on any specific model structure. You can use anything. If you want to use neural network, you can use. If you want to use deep neural networks, or if you want to use combination of neural network, deep neural network, recurrent neural network, I completely leave it to you. It's very generic. This first part was very generic. You can use any model structure, but the focus was on how to reduce the variance and bias. Any specific questions? Shanti ma'am?
Sir?
Any specific questions audience would like
Sir,
to
pose? As of now, no questions posted, sir.
Okay.
We will continue, sir. We continue, sir.
Audience also can ask questions now, if at all, if they want.
Hope participants not having any doubts, sir.
Oh, that's fine. So then that's great. I'll move to the next part.
Okay, sir. We continue, sir.
So in the second part of my lecture, again, I'm going to focus on, here the focus on how to build dynamic models. Those who are working, especially in the field of electrical engineering or mechanical engineering, or I would say chemical engineering, basically what they want to do is, like, before they want to understand the dynamic behavior of the system. Could be a reactor, or it could be a distillation column, or it could be a simple what I would say an converter, or it could be a simple RLC system. What is our interest is we want to capture the dynamic behavior of the system. Could be a dynamics of your UAV, unmanned vehicle, or it could be a distillation column, it could be a reactor, could be a simple low pass filter. Whatever be the system under consideration, we want to capture the dynamic behavior of the system. So for which we have to build dynamic models. So the approach again here I'm going to resort to is how to build simple linear models. So basically, I'm not going to build here a complex model. I'm going to build simple models at different operating points. By combining those non-linear models, simple models developed at different operating point, one can capture accurately the dynamic behavior of the system. That is our focus. So that concept is what is called local modeling. I'm not going to build single linear model, single non-linear model. Of course, I'm assuming that the relation between input and output are non-linear. So instead of trying to build single neural network model, which will capture the dynamic behavior of the system, I'm going to build multiple linear models. Then I'm going to combine somehow those models by assigning suitable weights to each model. As a result, I can capture the behavior of a nonlinear system. So I'm not going to use one model, single model. So bank of linear models will be used to capture the dynamic behavior of the system. The advantage is because the theory, the existing linear model theory can be used actually. So, and they're computationally efficient. It is easy to estimate the parameters of a linear models. And one can improve the accuracy by adding, if you want to improve the accuracy, you can add more models. Whereas if you try to build a single nonlinear model, if you want to improve the accuracy, it will be difficult. So, in nutshell, what I can say is local modeling is simpler than a global modeling. And we want to build simple linear models around different operating points, somehow combine them. And as a result, we want to capture the dynamic behavior of the system over wide operating region. And in certain regions, if the accuracy is not good, we would like to build models at those operating points. As a result, we can increase the accuracy. That's the focus. And so our interest is to approximate a given nonlinear system using multiple linear models weighted using a fuzzy membership function. Or it could be a neural networks as an interpolation function. You can use anything. Here again, it is very generic. You can use neural networks, or you can use fuzzy logic, or it could be a combination of neurofuzzy, could be a deep neural networks. So the networks are going to assign weights. I'm going to combine the models. Neural networks will generate weights. Output is nothing but the weights. And using the weights, I'm going to combine the different model outputs. And as a result, what I get is I can capture the dynamic behavior of the system. So here, so this function f, I would like to approximate with the help of n local linear models. With the help of n local linear models, we wanted to approximate this function f, and this hi of z of k is nothing but the weights. So here, this weights, I'm going to this weights. So basically, we have to assign weights to each and every model, and thereby you're going to combine the model. And for which one can use fuzzy membership function, or one can use neural network. Anything can be used. But here, the example which here I've chosen is a fuzzy membership function. And thereby, I'm going to combine different model outputs, and as a result, I can approximate this function f elegantly. So same thing has been depicted here. I want to approximate this nonlinear system. So in order to approximate this nonlinear system, I'm using n local linear models. N models I'm using. I'm not using one neural network model. This could be a local. This local model could be a neural network model which will capture the dynamics around this operating point, u1, y1. This is my first operating point. I'll build a model around first operating point. I'll build a model around second operating point. I'll build a model around nth operating point. And then each will generate output. First model output, second model output, nth model output. Now my neural networks of fuzzy logic, they are going to generate, they are going to assign weights to each model. So there are n outputs. So so I'm going to, so my W1 times Y1, W2 times Y2, Wn times Yn is nothing but my W1 Y1 plus W2 Y2 plus W1 Y1 is nothing but my model output. So I'll apply input to my model. It will generate an output. Then suitably it will be weighted. This weights one can get from fuzzy membership function, or from neural networks, or from deep neural networks. So thereby I'll assign weights dynamically. Let's assume if your system is operating around somewhere in between 1 and 2, then I'll assign equal weights. Exactly, it's halfway, 0.5, I'll assign. If it is operating close to first model, then I'll give more weights to W1, less weights to all other models. So by assigning weights, I'm going to combine linear models. As a result, I can capture the dynamic behavior of the system. So here, if you want, you can use for local linear models, one can use simple neural networks. Or you can even use here nonlinear models. You can combine bank of nonlinear models. If the system is highly nonlinear, if you're unable to capture using linear models, maybe let's say second operating point is highly nonlinear, I can build here a nonlinear model. First region, it could be linear, so I'll build a linear model. So again, the model structure need not be homogeneous, it can be heterogeneous. You can use neural networks, fuzzy logic, conventional models, and then on top of that, what I'm trying to do is I'm assigning weights to each model and combining this model. That's the power of this technique. So once you have, after having developed n local models, which will, and with the help of which, let's say we are trying to approximate a given system, the advantage what we have is we can build what we call it as soft sensors. And with the help of the soft sensor, they are nothing but local state estimators. With the help of the soft sensors, one can estimate unmeasured variables, variables which are difficult to measure online with the help of a sensor. Some of the quality variables, for example, top product composition and distillation column. And then purity, since something like purity, is what we call it as top product in a distillation column. Purity of any product, there are no sensors available. Through lab analysis, only one has to assess the purity of a product, purity of honey, purity of, say, any product. So for that, what we have to do is that now one has to infer using available measurement. With the help of available measurement, we have to build a relationship between unmeasured variable and variables which are correlated with unmeasured variables. I want to build a relationship between variables which are easily measurable and ones that are correlated with unmeasured variables. So I wanted to build a relationship between unmeasured variables and variables which are correlated with unmeasured variables, which can be easily measured, and thereby I'll build a model. So using that model, one can estimate the output of unmeasured variables. So that is also possible. So you can build soft sensors. As a result, you can estimate the unmeasured. You can generate an estimate of unmeasured variables, or variables which are difficult to measure online with the help of a sensor. So let me explain this with the help of this simple chemical reactor, continuous stick tank reactor. Let's not worry about the process. The governing equation of this continuous stick tank reactor is here shown here. The first one is a differential equation. So this is a differential equation. This is also a differential equation. Rate of change of reactor concentration with respect to time. Rate of change of temperature with respect to time. This is basically the governing equation of the CSTR. And you can see here exponential of minus E by RT. It's highly nonlinear. Exponential type nonlinearity. It's a highly nonlinear system. So if you are from a different background, what is more important here is there are two variables here, two output variables, CA and temperature, and there is one input variable which is QC. So you can imagine this basically as one input and two outputs. So input to the neural network is QC, and it will generate two outputs, namely CA and T. So we want to build a relationship between this T and QC. We want to build a relationship between QC and CA. So there is one input. And so by changing this, the input, basically, if you, in order to build a model, we have to conduct tests on the setup, or you have to simulate the model. So if you have a real experimental setup, you can conduct tests on the model, or if you have a model, then you can simulate. So like these are the input variations introduced. QC variation with respect to sampling time, sampling instance. So for this input variation, the system is responding. The variation in concentration, variation in temperature, here they are shown in figure. So if I increase the coolant flow rate, concentration is increasing, temperature is reducing. So this is how the system is behaving. And if I increase the magnitude of the coolant flow rate, what is happening is the oscillation is also increasing. More oscillation. From 98 to 103 to 107. If I increase the magnitude of the coolant flow rate, the oscillation is also increasing. So now, what we found out was basically this QC is the scheduling variable. With the help of this scheduling variable, we'll be able to assign weights to the model which we are going to develop. And we developed a multiple model. And here, what I've shown here is I've compared that multiple model output with the regress model. That is, the regress model is the actual model that is available. So the red one is the regress model output, and the blue one is the model which we have developed. And you can see here, initially there is difference between the model output and the actual output, process output. Initially you can see that, but after I would say 50th sampling instance, if you see here, the model output and process output are exactly matching. So as a result, what we can infer from this is, with the help of a simple linear models, by developing linear models at different operating points and assigning suitable weights, we were able to capture the nonlinear behavior of the system, non-dynamic behavior of the system. This is for concentration. On the right side, what I've shown is the temperature, how the temperature is changing with respect to time. There is some mismatch initially, but afterwards, the reactor temperature, that is almost the overlap. Process output and model output, the overlap, meaning the mismatch is very low. Let's say bias is very low. For input variations, what I mean by input variation is the Coulomb flow rate. Input is a Coulomb flow rate. We have changed this Coulomb flow rate. Corresponding to this changes, concentration and the temperature, they are changing. So the same input is given to the model as well as to the system, and we have compared the process output and model output. And on the right side of the bottommost, if you see figure, here the error is shown. Error at different sampling instant, almost you can see that it is lying close to 0. The error value is lying close to 0. So from this, what we can come to a conclusion is, with the help of a simple bank of linear models, one can capture the highly nonlinear dynamic behavior of the system. But so here, what we have assumed is both concentration and temperature are available. That means there is a sensor available to measure concentration, and there is a sensor available to measure reactor temperature. But in reality, concentration is difficult to measure online with the help of a sensor. So what is available is only reactor temperature. So with the help of a reactor temperature and the mathematical model, we developed a soft sensor. And so what is available to us is basically the temperature and the input and the mathematical model which we have developed. So using this, we estimated the how concentration is changing with respect to time. So as far as this example is concerned, I'm assuming that concentration is an unmeasured variable. It's not directly available for measurement. But I wanted to estimate this using the model and the available measurement. So available measurement is temperature, inputs, available outputs. I want to estimate unmeasured variable. Again, you can see here, initially there is some mismatch. Afterwards, almost the estimated value and the actual value are matching. So as a result, like we have developed a soft sensor, for which what is important, first we have to build a model. Then we have to use the available inputs and available outputs. Using the available inputs, available outputs in the mathematical model, we have estimated the unknown variable, which is concentration. And so in the models which we have used this simple linear model, one can use any model. You can use neural networks or deep neural networks, then you can capture the local behavior. So in here, if you see here, in the earlier one, what we have assumed is the feed temperature, because it has some more inputs, feed temperature, feed concentration, feed flow rate. Those variables also can change. So if it changes, how the model will respond? Will there be any bias? So for that, what we did is deliberately we changed the feed temperature from 350 to 352. Again, it was brought back to 350. And then we compared the estimated output with the actual output. Similarly, we compare the estimated value of temperature and actual value of temperature, and you can see that even in the presence of pulse-like variation in the feed temperature, the soft sensor is able to accurately estimate the reactor concentration, which is an unmeasured variable. Similarly, we assess the performance of the estimator in the presence of bias in temperature sensor. As I had earlier mentioned, only temperature measurement is available, sensor is available, but let's assume that it is not properly calibrated. As a result, there is a bias. And we introduce that bias deliberately at 258 sampling instant. And as a result, you can see that there is a difference between the red one and the blue one. So we introduce a bias, a sensor bias. On the right side, you can see that Y label is sensor bias. We introduce a bias of 0.5 degree Kelvin. This was deliberately introduced, meaning sensor is not properly calibrated. As a result, sensor output is not matching with the actual value, actual temperature. So in the presence of bias in the measured variable, whether the soft sensor is able to estimate accurately the unmeasured variable, which is concentration, that we checked. And you can see when we introduce a bias, initially there is a mismatch. Afterwards, the estimator is able to accurately estimate the unmeasured variable, which is reactor concentration. So in the presence of bias in sensor, in the measured variable, the estimator, that is the soft sensor which you have developed, is able to accurately estimate the unmeasured variable, which is reactor concentration. In the presence of change in the temperature, composition, also it is able to do, but here we have demonstrated for a change in feed temperature, it is able to estimate accurately. In the absence, of course, it is doing. So that's so essentially we have built a soft sensor, which is nothing but a model. Soft sensor is basically a model which relates unmeasured variable and measured variables. So using that, we have developed a soft sensor, and then which is able to estimate the unmeasured variable. That's the my second part of my presentation. So in the first part, like I had explained how to build a model, and in the second part, how to capture the dynamic behavior of the system by building simple linear models and combining those models, like by assigning weights to those models using neural networks or fuzzy logic or deep neural networks, or even the model itself can be neural network. So or a deep neural network, whichever, because some of the regions you will not be able to build a linear model, you have to build a non-linear model. So I won't build linear models, bank of linear models. A combination of linear and non-linear models will be developed. Somehow it will be combined. As a result, I'm able to capture the dynamic behavior of the system, non-linear dynamic behavior of the system. That is the part which I had focused. And if there are any questions, I would like to answer. So this is my second part of my presentation. The system could be, it can be a pH process, it could be a distillation column, or it could be in power electronics, say converters, or it could be an inverter. So, or in a mechanical engineering problem, it could be an inverted pendulum or an unmanned aerial vehicle, or it could be a heat exchanger. So depending upon the domain in which you are working, system can be different. But of course, what is more important here is system will accept inputs. There are inputs and outputs, and we want to build a relationship between input and outputs. So what is more important here is we can use different methodologies, and we came up with this methodology, like combining models using neural networks, fuzzy logic, and you can refer to our papers if you want to know more details, how we estimated the parameters, how we estimated the weights. Those things I have not explained. I'm explaining only the results. But of course, existing theories can be used because we are trying to build only linear models. So standard methodology proposed in identification literature, system identification literature have been used. We have estimated the models, the parameters also to the model, and we combined it. The novelty here is basically how to combine the models. So we have to assign weights and then combine them. As a result, we get low bias, low variance. Any specific questions with respect to the second part of my presentation? Hello. Any specific questions? Shanti ma'am, any specific questions audience have posed? Hello. Shall I proceed, ma'am?
Sir, excuse me, sir.
Yeah, tell me.
I'm Vijay Rajan, sir.
Yeah.
You were explaining about this B value, so W1, W2 B value in the previous first part.
First part.
Yeah. So there
Yeah.
are some negative B values. Is there any
Yeah.
meaning for negative values of bias B?
There is nothing to worry about, because those are all estimated values. B should be 0. Okay. Ideally, B should be 0, but you're getting some small value for B. Okay.
Okay, sir.
That is because of some error present in your measured value. When you try to acquire that, okay, that is because that is an irreducible error. That is random error. That is because of random error present in the measurement.
Yes, I can understand. So this whether this bias value is anything related to bias and variance, what we discussed?
No, this bias is basically a parameter.
Yeah,
That bias is basically if you apply, if your input is 0, what is the corresponding value of y? Okay. That is that bias actually. That is a parameter.
Okay, that bias is related to prediction.
The bias and variance, what I say is that that y tilde, okay, when you try y tilde and actual y, okay, the difference between the actual output and the predicted output is that bias.
Yes, sir. Okay, sir. Okay.
You should not confuse this with that. This B, this is basically that is for x equal to 0. What is the value of y? Y is B.
Yes, sir. I can understand.
That is a standard y equal to mx plus c. That's a very simple example. Okay, or this could be your bias in your. You can say this bias is nothing but, if you are using a neural network, this bias is nothing but the bias in the neuron.
Yes, sir. Okay.
In a neuron, what you have is there will be a bias, a firing strength, some threshold. Okay, it has to cross that threshold, then only the neuron will fire.
Yes, sir. I have another question, sir.
Yeah.
So we have this non-linear features, no, sir. Non-linear features, underfitting. Can we do anything with underfitting using non-linear features?
No. You should not. You can see what is important here is underfitting. You should avoid. You can do overfitting. As a result, what will happen? Your training error will be less, but testing error will be more. Okay. But what you can do is that using this concept of bagging, boosting, and thing, what you can do is that you can reduce the variability.
Okay.
So you can do a overfitting, that is no problem. But if you do an underfitting, what will happen? You need a low bias. Bias will be high. Okay, I don't want. So that means there will be much deviation between your output and. So as a result, what you have to do is that, okay, if you are using an underfitting, then in the sequential modeling, so in the boosting, you have to reduce the bias.
Okay.
So if you are in the next like in the boosting, what I said is sequentially you train the model. Am I right?
Okay.
So
yes,
so first model will yield a high bias, means then in the subsequent training, what you have to do is that you have to reduce the bias. So sequentially you have to train. As a result, when you train, the bias is getting ready. It should get reduced.
Okay, sir.
So ultimately, what is required is my bias should be low. That is more important.
Okay.
See, when I do a prediction, let's say a weather prediction, I have to predict the temperature variation accurately. Am I right?
Okay.
Okay.
Yes,
if my prediction is wrong, then obviously what will happen? No, the actual predicted value and actual value won't match actually, and it's of no use to public. It's of okay. So when you do a weather forecasting or a temperature forecasting, and now you know this, now the cyclone predictions and all, basically based on models. You have to use model and you have to predict. Am I right? When it will cross, so that we will alert the public, As a result, we can avoid deaths. So for accurate prediction, what is required is you need a very good, like this bias variance trade-off at the time of modeling. When you
Okay.
model itself, you have to take into consideration.
Okay, sir.
At the time of building a model, this you have to take this into a factor and build a model. But normally we won't do this. Normally, I have seen in most of them what will happen, won't worry about this bias variance trade-off.
Okay.
Okay, we will assume some model, some arbitrary model, and we will say we'll do a fitting,
Okay, sir. Okay.
but which has to be avoided actually.
Okay. Sir, can we avoid underfitting using nonlinear features?
Underfit, no, non-linear, no. Basically, I want to capture that feature. Right? Non-linearity also I have to capture.
Okay.
Okay, if you're doing underfitting, you're not capturing that actually.
Okay.
You should capture that non-linear behavior.
Okay.
Okay, that is our aim actually. Non-linearity also you have to see, for example, in this example, this relationship is not linear. The example which I gave, this example, if you see, it's relationship is it's not non-linear. I want to capture this behavior.
Okay, sir. Okay.
This relation is not a straight, and you can say it's not a simple line,
Okay.
simple straight line passing through an origin.
Yes, sir.
I would say a parabola.
Yeah.
So you have to capture this relationship.
Okay, sir. Certain tutorials I found that x1, say for an example, I have instance x1 and x2. If I want to have proper say regression problem, even I can go for x square, x1 square as a nonlinear feature, so that my regression can be improved. In that way, I found.
Exactly. That's what. But here in my example, I've assumed the wrong structure. I'm assuming that it will be function of x and x square. But my algorithm says no. Okay, w1 is going 0. As a result, y theta is function of x square. So the algorithm is able to correctly identify the model structure.
Yes, sir. Thank you, sir. Thank you, sir.
Any questions? Any other questions? Okay, so I'll move to the third part if there are no questions. The third part, so there are different nonlinear input-output model structures proposed in the literature. So I've listed those model structures first. Then how to represent those model structure using neural network is what I'm going to present. With that, I'll wind up. So these are the nonlinear model structures proposed in the literature. NARCS, NFIR, NARMAX, NOE, NSS. These are input-output model structures and state space model structures. NARCS stands for, if you expand the acronym, nonlinear auto-regressive exogenous model. This X stands for external inputs, AR for auto-regressive, N for nonlinear. Nonlinear auto-regressive exogenous model. X means exogenous means external inputs. Nonlinear finite impulse response model. Nonlinear auto-regressive moving average, AR for auto-regressive, MF for moving average, external input. Nonlinear. Nonlinear output error model. Nonlinear state space model. So these are different model structure proposed in the control literature to capture the relationship between input and outputs. So the process. So what I want to do is that I want to. So the process is behaving in a behaving a nonlinear fashion. So now what I want is that I want to approximate the nonlinear dynamic behavior of the system. So for which I have to use a model. So you can use one of the models. You can use NARCS or NFIR or NARMAX or NOE or NSS. But now, first, okay, so now what I have explained here is in NARCS model, YK, that is the output of the model, depends on its past values, YK minus 1, YK minus 2, YK minus n, and past values of its inputs, UK minus 1, UK minus 2, UK minus n. This is the model structure. Similarly, for NFIR, it will depend only on past values of U. So Y of K, output of the model, depends on only past values of U, UK minus 1, UK minus 2, and UK minus 1. This is NFIR model. And in nonlinear output error model, the output of the model depends on its past value. Y tilde is nothing but the output of the model. Whereas there, y is nothing but the output of the sensor. So here, y tilde k minus 1, y tilde k minus 1 means its predicted output. One past value of one past predicted value. So yk minus 1, y tilde k minus 1, U's are nothing but the inputs to the process. So in output error, so if you see in the first case, it depends on the sensor output, past value of sensor output, past value of the inputs. In the second case, it depends on only past values of inputs. The third case, it depends on the predicted value, past value of the past predicted values, and the inputs, past value of inputs. So then the inputs, what is more important is if you use neural networks, you have to, okay, which one to be used actually? Whether we have to use the sensor output or the predicted output. So this is very, very important. And in NARMAX, we use sensor outputs and then the past value of inputs plus the error. The error is nothing but the past values of error. That is the difference between the sensor output and the model output. EK minus 1, EK minus n. And in state space model, okay, this is the model structure. You have a state equation and a measurement equation. So X are nothing but states, Y are nothing but your outputs. We are trying to build a relationship between input states and outputs. In the case of neurons. So now, so these are the first I explained the governing equation, but let me explain now how to realize those equations using neural networks. The first one is NARCS. So in NARCS, I'm assuming that y tilde, that is the output, depends on only one past value of y and one past value of u. So as a result, what I can say is that it depends on only yk minus 1 and uk minus 1. You can see here yk minus 1 and uk minus 1. So y tilde is a function of yk minus 1 and uk minus 1. So as a result, there will be only two inputs in the input layer, two inputs. But of course, I'm assuming one hidden layer, you can use more than one hidden layer. I leave it to you. So if you want to improve the, probably you have to do simulation and see whether single hidden layer is sufficient or you have to use more. As a result, it will yield low bias and low variance. So hidden layers I'm using, and there is a bias that there are one hidden layer with two neurons. There is only one output because there are two inputs and one output. It's basically two inputs, uk minus 1 and yk minus 1, and output is y tilde of k. And they're all interconnected. I11, I21, I12, I22, these are all what I would say interconnection weights between input layer and hidden layer. And similarly, O11 and O21 are your output layers. So there are totally around 8 parameters: I11, I12, I21, I22, B1, B2, O1, O21, and then you have a bias in the output layer also. So there are around 9 parameters to be estimated. So you can use any like a backpropagation algorithm, or you can use Kalman filters, extended Kalman filters, unzended Kalman filters. So for training neural networks, there are many methods available. You can pose it as an optimization problem. Like for example, regularization, this concept of regularization, because these weights are all, okay, these are all weights. So you can use regularized approach, and then you can estimate the parameters, and thereby, and then you will do a validation. Okay, and of course, you have to select the right activation function for the neurons in the hidden layer. Similarly, activation function in the output layer. So all this one has to do, and then and thereby you can approximate. You can capture the dynamic behavior of a nonlinear system. That is in the case of NARCS. In the case of NFIR, as we know, it depends on only U's. So I'm assuming that it depends on only UK minus 1, UK minus 2. So as a result, what we have is there are two inputs in the input layer. I'm assuming there is only one hidden layer and one output layer because there is only one output, and the same connection weights. So again, you can determine the weights using backpropagation algorithms, or because it's a feed-forward neural network, or you can use I would say You can pose it as an optimization problem, estimate the weights, or you can use Kalman filters, extended, unscented like filters, and then you can estimate the weights recursively. So there are many methods available for training neural networks. So with the help of this, you can capture the dynamic behavior of the system. Then you can use nonlinear output error model structure, where here I'm using the past values of the output. Here, this is basically a recurrent neural network. I'm feeding the output of the neural network back to the input actually. So this is basically a recurrent neural network. It's not a feed-forward neural network. UK minus 1, y tilde of k minus 1. These are the two inputs. Connection weights, of course, I'm using one hidden layer with 2 neurons. So now number of weights between input layer and output layer, if you see I11, I21, same thing. So same 9 parameters, but this is basically a recurrent neural network. So you have to use back propagation through time, the correct algorithm you have to use, and then you have to train the weights, and then you can carry out predictions. In the case of Normax, we have to feed this epsilon is nothing but the error between the actual output y and y tilde. So epsilon k minus 1. So there are 3 inputs here: uk minus 1, yk minus 1, and epsilon. This epsilon is nothing but the difference between. That is very important. Okay, so that is there are 3 inputs. This epsilon is nothing but the difference between y minus y tilde. As a result, number of parameters, because we have to connect this epsilon to hidden layers. This input also has to be connected to all the hidden layers. So it's a fully connected layer. So I'm assuming, but the algorithm, probably what will happen, it will try to establish. Suppose let's assume that this I31 is 0, then epsilon is not function. It's not going to affect H1. Like W1, I said W1 in the earlier case has become 0. I'm assuming that it's a fully connected network, but when I estimate the weights only, I'll come to know whether it's a fully connected network or partially connected network. And similarly, in the state space model, we won't feed the output of the neural network back to the input. Here, the hidden layer output is fed as an input to the neural network. So this, the XK, the output of the hidden layer is fed back as an input. Actually, so that is basically a state space model. So you have different model structures. So the person who is going to build a model has to select the right model structure, and then he has to estimate the parameters also of the model structure and do a validation, and thereby he or she will be able to capture the dynamic behavior of the system. So, like popular methods, I would say training methods are Kalman filters. You can use extended, unscented Kalman filters to estimate the weights of neural networks. And then you have to, of course, you have to do validations. You have to check whether the testing error, validation error, all that you have to determine. For that, you have to use only mean squared error. So, and then check if there is any substantial variation in the training error and testing error. If so, then what you have to do is that you have to do regularization, all this, and thereby. So I'm not going to explain in detail about training the neural network. Especially if you use deep neural networks, number of layers will be more. So as a result, number of parameters will be more, and you need more observations, more data points. Otherwise, what will happen? You will not be able to accurately estimate the connection weights. As a result, the model that you generate will not yield low bias, low variance. So these are very, very important. And with this, I would like to conclude my presentation. And if there are any specific questions, I will answer. I'll be able to answer. Of course, we have time. We have another 10 minutes. If there are questions, I'll answer. Otherwise, I would like to wind up my lecture. Shanti ma'am?
Sir, participants having any doubt? Hope participants not having any doubts, sir.
Okay.
On behalf of myself and all the participants, I thank Dr.
J. Prakash, Department of Instrumentation Engineering, MIT Campus, Anna University, for providing the depth knowledge in data-driven model and machine learning. Hope this session gave a better perception for how this mathematical derivation really formative for our research work, and also lay the foundation for mathematical concepts used in data-driven model. You have clarified the participants' doubts patiently, sir. Thank you, sir.
Okay, thank you very much, ma'am. And I wanted to thank each and every participant for having patiently listened to my presentation. And I would like to thank the organizers for having given me this opportunity. And I wish all the participants a very good luck. Thank you very much.
Thank you, sir.
Thank you. Shall I leave, ma'am?
Yes, sir. Yes,
Okay, thank you.
Thank you for participants. The feedback link is posted in the chat window. All are requested to fill the feedback form. We will be back at 2 p.m. sharply.